So as far as I understood, this is the fourth lecture of working in group seminar. And Jean asked me to explain, well, he was concerned about the connection between probability and operator formalism. So you asked me to explain this link and to end with the spectral resolution using operators for the Liouville Hamiltonian. So this is what I'm trying to do. And this is, I think this is the first touch of the blackboard in my life. Okay, so let me just recap. I asked the background you had on the first three lectures. So if there is something that is not clear, you stop me. Perhaps I will recall that a few things and explain the philosophy of why I will tell you something about this Hamiltonian. So, so here you have you want to define a conformal field theory. So basically, you have to start with. Our starting point was a Riemann surface with a metric, Riemannian metric, and then you will have mark points at some point. But if you forget for a while about the mark points, on this Riemann surface, you have a path integral, so you have a test function R maps to a quantity, which is an integral. So this integral has integration variable maps that are defined on the surface and taking values in R. And this action that you've got here is the Liouville action, so S sigma of G phi, so it depends on the metric, is equal to 4 pi. You have the gradient square and the metric G, plus a curvature term. So R is the richest curvature on the surface. So you have this quantity here that you integrate with respect to the volume form Vg of the metric G on the manifold. Here mu is a positive parameter. And since this theory has a scale with respect to mu, you don't care so much about the mu. You have a parameter gamma between 0 and 2. And the Q here is also a real parameter. It's gamma over 2 plus 2 over gamma. Okay, and what we want to compute are correlation functions. So it amounts to choosing a specific f in this picture. So now you play with the mark points. So you have mark points on the manifold. To each mark point, you attach a weight. And all the weights here, you have alpha 1 and alpha n. And you can take them real to start with. And you want to compute correlation functions that are usually done this way. So the correlation function depends on the choice of the metric. And this is basically, at least formally, the path integral evaluated at products of exponential ways. Okay. And the philosophy, so in the next talk, Colin will talk about amplitudes. So basically the amplitudes are, you will decompose your surface, so basically into pair of points. So you will make some cuts on the surface to split your manifold into pair of points. And you will restrict this path integral to, say, this part of the manifold, with the field being integrated here, being conditioned on taking some boundary values along this circle. Okay? So this will be called amplitude. So you will have one amplitude on this side of the manifold, one amplitude on this side, and you will glue them together to recover the whole manifold. Okay, and this gluing will be performed by integrating over some Hilbert space. And this is what I'm going to describe now, okay? And what I want to end up with is some kind of Plancherel formula for this Hilbert space. Okay? So, and to grab this Plancherel formula, I want to introduce some operators. Okay, so so the Hilbert space I want to play with is a space of function. So I will consider a trigonometric series on the unit circle. So I will single out the zero mode of this Fourier series. So this field is real values. This means that you have a phi n minus n. And I will use other complex coordinates. So here, this phi n, I will write them as xn. So xn and yn are real coefficients for n positive. Okay, and for n negative, you use this relation to parameterize your coefficient. Okay, so the space I will be interested in is the Sobolev space, say H minus T is the unit circle. It's the set of those functions such that the sum over n of the phi n squared okay, so this is a Sobolev type space with a negative index. Okay, and then I want to equip this space with a measure. So here on the zero mode, so this guy lives in the real line. I will define a measure that I will call mu. This is the Lebesgue measure on the zero mode, tensorized with a probability measure P, and this probability measure is Gaussian measure. Under this measure P, that just means that the coefficient xn and yn are IID Gaussian. Okay, so this is basically the tensor product over n of exponential minus. So the Hilbert space in the end is just Hilbert space that I will denote by H is just the L2 of the Sobolev space equipped with the measure mu. Okay. So basically under this law here, the series that you've got here is the GFF, the Gaussian free field restricted to the unit circle. Okay, that's it. This is a Gaussian process. And now I want to play with dynamics to define operators. And so Jean asked me to start with the GFF dynamics, so with no potential. So what I want to do now is to introduce. So if I will now consider the unit disk G, and if I'm given such a field phi, phi will be harmonic extension of phi to G. Okay. And I will also consider the Dirichlet GFF. So basically, this is a Gaussian distribution with a, so it is centered, and remind you of the green function. Okay, so this is a Gaussian field, a Gaussian function, and you can evaluate So it's characterized by its green, its covariance kernel, and it's given by the green function of the Laplacian with Dirichlet boundary condition on the unities. Okay, so now I want to use these two guys to define the semigroup on the Hilbert space. So the semigroup. So f is a test function, a measurable function defined on h minus s, and it will be an expectation.
So just to be clear, this P is the same as the Gaussian proof field restricted to the
yes
line that's
yeah, exactly. I will explain which expectation I'm taking here, because if I take a Dirichlet GFF here, this means that I have another probability measure for this guy. I'm going to explain the notation just in a minute. So now what I'm doing is that I will evaluate the Dirichlet GFF Okay, so here I have two fields, the phi here is fixed, and I have a Dirichlet GFF, and I'm integrating over x, only x.
The problem in STF of phi.
Yes, sorry. It's a function of phi and phi. So here I'm fixing the field and I'm integrating over x. This means that I condition on phi. And I'm looking, basically what I'm doing here is that this field x plus p phi is, you can think of it as a function defined on the disk. And I'm just looking at its values on the circle of radius p minus t. And I see this function on this circle as a function on the circle. Okay. So this gives me a new element in the Hilbert space, and actually this guy turns out to be a semigroup. Okay.
Sorry, what is capital F?
F is a test function, if you like. You define, so F belongs to H. Okay, so turns out, so you're just looking at this dynamics of shrinking circles, and what this dynamics gives you as function on this shrinking circles. Okay, is that clear?
So what you are doing is you are fixing a t.
I'm fixing t.
You are fixing, and then you map the t into the unit circle. Then
yes.
You look at how the thing works.
Yeah, and I'm looking at this is a function on the circle, and it has it's a different function on the circle now. And so this is an operator sending f to STF, and turns out that this is a semigroup. And you can compute its generator, so it's a self-adjoint semigroup, and you can compute so ST is equal to exponential.
The expectation is taken over X, or what is the expectation?
Yeah, this means that I condition on the field phi. So expectation is with respect to this guy here. Only the Dirichlet GFF is integrated over. And here I think I forgot just for to connect with the following. Here I forgot to add this trivial factor. Okay. So you can compute the semigroup, and in the coordinates written here, you can write this guy as h is equal to minus, so 2 times derivative in the 0 mode plus sum over n. So in this, if I see this coordinates as as parameterizing my Hilbert space, I can differentiate with respect to these coordinates here. Here, the star means I take the adjoint with respect to the Gaussian measure of the partial derivative in Xn. Same for Yn. And plus a trivial shift q squared over 2 coming from this guy. Yeah. So basically, for probabilist, what does that mean? It means that you have a dynamics on the modes of this field. Over the zero mode, this dynamics is just a Brownian motion. On the components here, this is just independent of Shannon-Lenbeck processes. Okay, so the dynamic is completely trivial. Okay, all the Fourier modes are independent under this dynamics, and this guy is the Hamiltonian of the QGFF. And actually, you can try to decompose this to find an orthonormal basis for this guy. Diagonally, this guy. So the eigenstates. So I will consider to diagonalize this space. What you have to find the eigenfunction of this guy here, multiply by the eigenfunction of each of the guys here, and take the product. You will get a basis. Okay. So if I denote by k a sequence of integers, which is 0 starting from some rank, and same for L. Okay, you can get the eigenstates. I will denote them by PQL. So for the Laplacian on the real line, you just get this exponential. And then you have a product. So to diagonalize the harmonic oscillators here, you just have to consider Hermite polynomials and take the product of Hermite polynomials. Okay, so we get product of Hermite polynomials in each variable. Where here Kn is just the degree of the Hermite polynomial. Okay, and this way you get a basis for the H. The eigenvalues. So if you look at this guy, the eigenvalue is just q squared plus p squared over 2 plus the what I denote by k same for L is just the sum of over n of n kn and the same for L. So this is just a simple computation. So basically, this means that if you are familiar with the Heisenberg algebra, this means that to get this Hermite polynomial, what you see this guy here is named creation operator. You apply successively the creation operator to the ground state here, and then you form the eigenstates of the free field by applying successively to the ground state the creation operators. Okay? And you find this guy, this Hermite polynomials. Okay, this is a trivial thing for the GFF, but this is not what you want to do here. You have also a spectral resolution attached to this orthonormal basis, but this is not the one you want to use because they are not adapted to the symmetries of the problem in CFT. You want to change the basis, okay? And I will explain how to change the basis using again probability theory, okay?
Here P is the real number.
Yes, sorry, P is a real number. P. And it's on the real line, the one real line. Yeah. So So now I'm going to still play with dynamics, but I want to create other operators. So to do so, I will consider flow of holomorphic deformation. What I mean by that, so now I want to take a vector field V on the unit disk. And I will specify, so I will specify two things. V, I will take a V of the form epsilon, a complex number, but small. So if I have a vector field, I can look at its flow. So this flow is just a family of holomorphic function indexed by by t at the time, which are defined by this flow here, and starting from identity at time 0. So what I want to do now, if you look at the unit disk, here I had looked at the restriction of the GFF on shrinking circle. Now, instead of shrinking circle, I will look at the image of the unit circle by F. This function ft, it's a holomorphic function on the unit disk, and you can look at its image. It forms a loop in the unit disk. So so it's not clear that in grid generality, it's not clear that at positive time f sends the unit disk inside the unit disk. But if you take epsilon small enough, then it's true that you're mapped into the disk. And
it's exponential minus t in this case. If you take epsilon equals 0.
What?
If you take epsilon equals 0, then
yes.
It's just exponential minus tz.
It's a particular case. So how you recover the previous case? So you can take, if you like, epsilon equal to 0. Then V, your vector field is just minus z. And ft of z is just exponential minus t z. Okay, and you recover this way the flow upstairs. So I want again to define a semigroup with this guy that will depend on v. So f is again a test function. And I will form the expectation with respect to the Dirichlet GFF here of f. So now, instead of looking at the Dirichlet GFF on the circle, I will look at its image on this red curve. Then there is q log. Okay, so this is still defined on the disk, but I will look at its restriction to the unit circle. Okay. Is that okay?
Sorry, can I just understand the relation between this STF and your integral, what's it called, path integral picture? So is the picture meant to be, if I take a surface with this boundary circle.
So the picture here.
Yeah.
Okay. Here, what I'm trying to avoid is the notion of amplitudes. And what you will consider is that when you will do the amplitude that are related to these operators are the yellow area here. So basically, this will be the path integral restricted to this yellow area and conditioned on its values on the white circle. So basically, you can interpret what I'm saying you in terms of conditioned path integrals. It's not completely clear from my.
Okay, go ahead.
Recall me to come back to this point.
Maybe you can say that, so this ST of f, it has an integral kernel in this Hilbert space. So you can write an integral kernel.
Yes.
And the integral kernel is going to be a path, it will correspond to a path integral of this annulus, this yellow annulus. You integrate over all field on this annulus somehow.
But your capital F, it was something that you could put into your path integral there, right, on a surface.
No, it's not the same.
It's not the same. So basically, the thing is that okay, I'm making a stop. So so A means amplitude. Amplitude is a conditioned path integral. Let me just write this for the moment. Yeah. Formally, this is you can write this ST this way. So this is the integral kernel of your operator, and if you look at this integral kernel, then this amplitude is the path integral phi that you condition on the two curves. So you have one curve here, C prime here.
Yeah, okay.
It's not the same f, it will correspond to f, big F there, it's like 1 somehow.
But I think you could take this big F to be like isn't this H meant to be the possible observables on this?
Yeah, you could take this F here equal to this F here, but restricted on the circle, on the circle here. Yeah, so I wanted to. I was not sure you had a lecture on the Sega amplitude,
Okay,
so I skipped this point in presentation. But good to ask. So yeah, it's indeed related to the amplitude, but in this case, you can prove that. So the generator of this case, so this is again a semigroup, provided that epsilon is small enough. So there are assumptions, but say for epsilon small enough, it's okay. So you have a generator. And this guy here, it's equal to, let me put a 0 here. So it's equal to H0 plus epsilon. Plus the sum of two operators, okay? You can check that you make some computation, you compute the generator, and the generator is the sum of this guy here, plus two additional terms that are given terms of operators. And these are these operators I want to describe now a little bit more. What I'll say. So basically, this guy will be the Virasoro generator for the free field. I can. So first, you have an explicit formula for L0 n and L2. So this is minus always forget this expression. Need my laptop. But basically, what I can try to explain is you recover the. I don't know if you are familiar with representation theory, but this is a Sugawa construction of the Virasoro generators starting from the Heisenberg algebra. Okay, so it's better to write it this way, at least for me. For some operator A that I'm going to describe. Okay, I will explain in a moment what these dots, double dots mean. So what are these AN? So for n positive, these AN are just expressed in terms of the partial derivative with respect to the coordinates. So A tilde is the same stuff with the plus. So for, and then you have, so this gives you the values of the n for n negative, for negative n's, same for A tilde. I forgot here, you don't have the A0.
Sorry, what is that alpha superscript?
This is a star.
Oh, stop.
Yeah, this is the adjoint with respect to the Gaussian measure. And the same for A T0. Okay, so these operators, actually, they satisfy some commutation relation. So you have AN, AM. So the Lie bracket here is for the commutation relation. So it's n over 2 direct mass for n equal m. And you have the same relation for. So what's the message here in this blackboard? The message is that you have a construction in representation theory telling you that if we have a representation of the Heisenberg algebra, then you have a way to construct some operators associated to another algebra, which is called the Virasoro algebra. And this construction is the Sugawa construction. Okay. So basically, this picture here means that you have a probabilistic representation of this Sugawa construction. Okay. So why are this? Is that clear so far? Questions?
The D on that A tilde on the right.
Sorry?
By the YN, I think it should be DYN.
AN tilde equal to square root of n.
Here, there is a partial relation. What's the question? What was the question?
That's the question.
Ah, that's a typo, yeah, sorry. So typo. So, and this operator from I want to keep this blackboard, so perhaps I will erase. So this operators form a representation of the Virasoro algebra. Actually, we have two representations. Here, in the same way, here we have two representations of the Heisenberg algebra, actually. One for the A and one for the A tilde. Okay. And so, you have two families, LNs and LN tildes indexed by Z. So for now, what I forgot to mention here is that N has to be positive. Okay. I only have a positive modes. So here I haven't still defined what are the negative modes. So the negative modes are just the adjoints. So okay. Yeah, you take the adjoint with respect to the Gaussian measure. This family commute with this one. And you have a commutation relation, a non-trivial one within this family, and exactly the same for this one. If you look at the commutator between L0n and L0m, you get something n minus m, L0n plus m, plus so central charge over 12. Identity. Well, here, this number here, the central charge, you have an important number. In my case, the central charge is 1 over 6, 1 plus 6q squared, where q was this number here. Okay, so this family of, what's important for this family of operator is this commutation relation. Okay. So this is a way of encoding the symmetries of the probabilistic objects in a different manner. Okay, so you have a representation of this Virasoro algebra in terms of these operators. Okay, so this is the way you can see the Virasoro algebra in the probabilistic setup. This is only for the QGFF. And one important thing is that this Hamiltonian H0, here you can see it as the sum of L00 plus L0 tilde 0. Okay, this is the sum of the guys number 0 here and here. So now you can play with these Virasoro generators to form a basis of your Hilbert space. So you have a complete family proceeding this way. So I will denote them by psi q plus ip nu tilde, where nu tilde are Young diagrams. And the Young diagrams are just finite sequences of positing and decreasing numbers. Okay. So why do you use these Young diagrams? First, the first point is that if you start from empty Young diagrams, you can recover the whole other guys with the same label IP. So this means that psi q plus IP nu tilde is equal to. So these guys encode the way which Virasoro generators you will apply to the ground state to get this guy here. Okay, so you get L0 minus U1
So how did the Young diagram, what's the parameterization going between
I'm going to
the K and L?
Sorry?
So over there you parameter
the
free case by some sequences K and L.
Yeah, this was to encode the Heisenberg algebra.
Yeah.
So this were sequence of integers, but they are not related to this Young diagrams here. These are not the same here. This is not Young diagrams. It's just sequences of integers. They cannot be decreasing. They could be not decreasing. And here, so new. Here you have this constraint here. And same for new. Maybe I can comment a little bit more on that. So that you apply to the ground state here. Okay, the ground state just means that you take empty Young diagrams. And why can you? So imagine you have you can apply Virasoro generators with non-decreasing sequences, but then using the computation relation, you can compute the guys to order them. Okay, and so you can basically you can reduce to this situation here where you're indexed by Young diagrams.
So you could do the same thing in the free case, right? You just get a different basis for the same.
For the free case, you can.
But you apply the creation operator instead of L.
Yeah. So these you could do the same thing as this over there. You just get something different.
Yeah.
This is what that he does actually for the H already. You apply some creation operator, for example, to 1.
Yeah.
Okay, maybe the ground state you didn't write is exponential IPC.
Yes, it's written somewhere. So ground state, you take here the ground state is the same for Heisenberg. You just remove this guy. You take empty K and L, and you are just left with this guy here.
So this phi 0 there is the same as this.
Yes, the ground states are the same. So you have here if you look at H0 applied to. So this is the Hamiltonian, the generator of dilation. If you apply H0 to this guy, here you get an eigenfunction. So the eigenfunction is, the eigenvalue is q squared plus p squared over 2, plus the length of the Young diagrams. And in this case, the length just means the sum of the news. Okay, this is a bit different than there. Psi q plus ip. No, and there is a subtlety if you write the associated spectral resolution, is that these guys here are not orthogonal. Okay, they are orthogonal for different p's, but if you fix the p and you look inside the Werner module, if you like, they are not orthogonal necessarily depending on the values of the Young diagrams. Okay, so this way you get a spectral resolution. This means that you can write Plancherel formula on your Hilbert space. Maybe there's 1 over 2 pi. You have to sum over Young diagrams. So this means that I sum over Young diagrams with the same length. Okay, so and I have integral over the real p's. There is a prime, yes. But then, since they are not orthogonal, they are Gram-Schmidt coefficients. So let's write them as Q.
We're missing the G.
Yes. And there are Gram-Schmidt coefficient that, let's say Gram-Schmidt. This Gram-Schmidt coefficient depends on mu tilde and p. Well, they depend on the Young diagrams, p, the nu tilde, the nu primes. I don't write the explicit form. This is called something that is called the Shapovalov form. Okay, you can compute them. It's a subtle thing, but well, they are just Gram-Schmidt coefficients. Okay, so you get your spectral resolution, and it's more adapted to the symmetries of the problem. And now this is what you can do in the GFF. Okay, this was the first step you wanted me to discuss. Now I can explain. I can try to generalize to the Liouville CFT the difference. So I kept all the blackboards, and I will write the differences in red. So first, so you still start from the same Hilbert space, but I will add a potential. Okay, so the first guy I need to modify is this one. So here, I will add the potential. So you can think of this formula as a Feynman formula. So if I add the potential in the, this is a Laplacian, infinite dimensional Laplacian, this is a Laplacian. I will add a Schrödinger type term, if you like, potential. And so if you think in terms of the Feynman formula, I'm just pushing something in the exponential here, okay? So this will be, let's call dt the area here, I call it dt. So I'm integrating over dt the Gaussian multiplicative chaos I think you had a short lecture, Gaussian multiplicative chaos. So here I'm taking the exponential of the JK GFF plus harmonic extension. And I'm integrating over this red area here. And so if I'm just playing with the Feynman formula, I'm adding a term here, which is, so there is a mu here. I'm adding mu, a potential term, which is the Gaussian multiplicative chaos integrated over the circuit. And this term here acts by multiplication. Okay. So now it's no more 0, but mu that I want to put as index in the Hamiltonian. Okay, so the Hamiltonian now depends on mu. For mu equals 0, you recover the guy we were working with just before. And now I have this potential, and this what I want to diagonalize now. Okay.
Maybe you could say it's a positive LP function.
Yeah, this potential is positive, but it's a very wide function. For those who know GMC, you know that it only makes sense as a random variable for gamma less than the square root of 2 because we are on the real line. So between square root of 2, it's a bit more complicated to play with this guy for higher gammas. There are some subtleties here. Okay, so this is to define the Hamiltonian. So you still get a semigroup, it has a generator, and you can compute it. This gives you the Hamiltonian of Liouville theory.
So what was, before you had a Q though? Okay, so before you put in this mu, you had a Q.
This Q here?
Yeah.
Yeah.
What were we computing then? Because
it's a trivial, you mean?
Well, I'm just confused. It wasn't a free field because there's this Q parameter.
It's called the Q free field. You have a little shift in the Q to move the central charge.
Oh, I see.
So even with the GFF, you can, well, usually, I don't know if it's your question, but usually people say GFF has central charge 1,
Yes.
but you can play with it, with the Q, to create a new central charge.
Ah.
Okay, so I was just playing with the Q to move the central charge to 1 plus 6Q squared. You can move with the Q the central charge. So, so for the flow of holomorphic deformation. Let's call this area HE. The yellow area HE. And I'm going to modify this guy in the same manner to get another semigroup, but associated to other possible deformations. Here, this was for dilation. Now I'm playing with holomorphic deformations. And inside here, I'm plugging an additional exponential term, exponential of minus mu, integral over this yellow area here, exponential gamma x plus p5 plus harmonic extension, integrated with respect to this measure. Okay, I'm plugging this further exponential term inside. Okay. And this way, I can again compute for small epsilon the generator of this semigroup. So now I have a mu instead of being in the free field case. And I have that my HV mu is a sum of the Hamiltonian of the Liouville theories, I mean this guy, plus some extra terms that are now the Virasoro generators. And I will just skip the mu. Okay? So these are now Virasoro generators, but in the Liouville theory. Okay. They satisfy so exactly the same relation here. Except that now we have mu here. So the Hamiltonian. So I have a family defined this way.
The link between ln0 and ln mu kernels.
Yes, but later, in one moment. Okay, so I have this generator. I have, and I observe that it gives me new operators, ln's, and you can see that they satisfy the same pictures. So the Hamiltonian of Liouville theory is the sum of the terms number 0, and then you have the Virasoro relations. So yes, so now what are the relations between these guys and the free field guys? Actually, I want to keep some blackboard. Okay. I can erase Heisenberg. So, well, what you can prove is that actually Ln is the sum of L0n plus a potential, and this potential is mu over 2 integral over the circle of exponential I n theta. So it's a GMT type additional term. No, sorry, the C is in the field. Okay. So you have this is the sum of the free generators plus an additional potential. Okay. And now you have this family of operators. You want to play with them with this guy here to diagonalize this edge. Okay, so but now the game is a bit more difficult. So how do you construct the Eigenstates? So now the computations are not obvious. So first, you have to define some operators. Okay, so if you remember the shape of the potential H was H 0, so this was the free field Hamiltonian, plus exponential gamma c. And we want to construct the eigenstates. So there is a non-trivial thing.
CFT doesn't have the zero model.
Yeah, okay.
You should write phi equals c plus.
Yeah. Better to write this way. So, and phi, I just single out the because we'll try to explain something. So you construct a map, the Poisson operator. This will be a map that will send the free field eigenstates indexed by Young diagrams. Each time I'm plugging in this Poisson operator a free field eigenstate, it will give me something that will be in the end an eigenstate of H in the following way.
Sorry, is there a factor of mu there?
Sorry?
Is there a factor of mu?
Yes, yeah, there's a mu here. Thank you. Okay, how do you construct this? Well, you can construct this guy as an eigenstate such thing with this relation. I'm going to explain a little bit where this comes from. So you want to diagonalize this Hamiltonian, and you see that you have here an exponential weight. Okay, so if you look at if you plot a picture, just this exponential weight here for c minus. That's two important features. First, you see that it vanishes when the c goes to minus infinity. This way you expect that that the eigenstates, when the c close to minus infinity, they will look like the free eigenstates. Okay, but then you have a wall here, a very containing potential. This means that plane waves, IPC, when you move forward, they will be reflected by the wall. And they will come back the other way. So that it turns out that if you want to construct the eigenstates, you will say, okay, let's fix a free eigenstate when we are close to minus infinity. So try to find how it is reflected by the wall, and this is in some way the reflected coefficient. So if I impose close to minus infinity to be of this shape, there is a unique guy here. That corresponds to the reflected term, to the reflection of this term here, plus correction. You can see that you can construct this guy with this shape. Okay, and so this is a non-trivial fact. This reflection coefficient, I won't write it, but it's explicit in terms of gamma function. And you can also show that if you look at psi p nu initial, actually it's the same up to something, up to an explicit coefficient, the same as the reflected guy. This is different from the free field theory. Here in the Liouville theory, you just the spectrum is just the positive line. Okay, because of this confining potential. So, and now you can show then that, and it's not, I'm almost done. You can show then that the last feature of this guy is that you can show them playing with the probability theory. You can show that these guys are just Virasoro generators with the same notation as before. Where you apply the Virasoro generator to the ground state. And then you get spectral decomposition.
Is the ground state still that simple formula, or it's now more?
So the ground state, so this is a very good question. So let me write, okay, so the point is that, let me draw a picture. I don't need this blackboard. So if you look at the point is that for this eigenstates, we have no probabilistic representation. This is a completely an analytic statement, and we are completely stuck to using a probability theory. So what we do is that, so the spectrum, here we have the line of the Q plus IP, and on this line, we can, we have all these guys here. The P, I'm just encoding the P in my plot, okay? So we have this line here corresponding to the spectrum. The first thing we do is we prove that we can analytically continue this eigenstates to the whole complex plane. Okay? So this guy on the spectrum, they have an analytic continuation to the whole complex weights. Okay, in the same way that if you look at the eigenfunction of the Laplacian exponential IPC, you can extend them. Okay, so we have a theorem that tells you that you can interpret this guy as a restriction to this line of some holomorphic function on the complex plane. And then there is a probabilistic region here. Around this region, here we have a probabilistic representation. Okay, so the whole game is to have an analytic theorem, analytic continue, enter the probabilistic zone, play with the probability to have obtain a relation, and then continue them back to the spectrum line. Okay.
And the probabilistic expression is similar to the ST, it's conditional expectation.
And so if you, for instance, if you enter the probabilistic region, you have a simple expression for the ground state, actually. The descendants are more complicated. But so you have exponential alpha minus Q C expectation, conditional expectation on phi of exponential of minus mu integral over the disk exponential gamma x gx initiates so this means that I'm only integrating with respect to x. Okay. Actually, here I have removed the zero mode from the boundary field using this this here. So you have a probabilistic representation for the eigenstates, at least the ground state, and but also you can have a probabilistic representation for the descendants, but it's more complicated. So yes, the whole game is to establish all the combinatorial relation we get. We obtain them in the probabilistic region. So we move from this line often to the spectrum line and back to obtain the combinatorial expression here and then move them back to the spectrum line. Okay. And once you have established this theorem, you have the same spectral decomposition, okay, using now the eigenstates of the Liouville theory with the same Schmidt coefficients corresponding to the Shapovalov form.
The integral is R plus.
And yes, the subtlety here is now that the integral is R plus in the Liouville theory because of this reflecting work. I think I'm done.
We'll have to move soon to Cohen's talk. Maybe just one thing just to clarify. So this inner product FG, this decomposition, then you use this, for instance, on a 4-point function to get the bootstrap, if you will, just to connect with.
Yeah, actually, what's important here is actually that the spectral decomposition is really the way you make sense of the operator product expansion.
Okay, yes.
Yeah, you can, for instance, you can try to, well, if you just, this means that formally you can write a state as a sum over this basis here.
Yeah.
And the coefficient that you got in front are just the coefficient of the OP in physics. So this is really the way you can understand OP in this
And
framework.
these Gram-Schmidt coefficients and go into the conformal blocks.
Yes, they are going to. But then Colin will explain because there are Gram-Schmidt coefficients, but then other terms that comes from the Virasoro symmetry. There are not only the Gram-Schmidt coefficients in the block, there are also all other terms coming from the contribution of descendants, and they come from symmetry. So, but Colin will tell you more in the next talk about this.
Okay, yeah. Okay. Maybe we thank Rémi again so we can move.